All right. Well, good morning. We have been working on the solution to the free particle problem, and we had this free particle solution which had the form uk of x e to the minus e sub k t over h bar, where this uk of x was e to the I kx, and therefore this term here brought in e to the I h bar k squared over 2mt. Okay, so this is the form of the wave function for the free particle, and we learned how to expand any general initial condition in terms of these things. Now, a few things regarding the velocity of the wave. You see, if I look at the velocity of the wave, our standard way of doing this is looking at e to the I k, x minus, I have the, let's see, I factored out the k, so it's going to be h bar k over 2m times t. Okay, so over here you see I get something which looks like momentum over twice the mass. Okay, this may be a little surprising because we expect that the free particle moves with some velocity. If we want to associate the velocity, the classical velocity, it should be p over m, but I have a p over 2m here. Okay, that's because we are looking at a pure wave which is propagating in space. But if I have a combination of waves, okay, so if I have, if I just make up a what's known as a wave packet, so that I add many of these things, okay, using the Fourier transform, so I get something like that. Okay, so this is the velocity with which this wave front is moving. This is called the phase velocity. We'll denote it as Vp. Okay, this is the phase velocity. And it's equal to p over 2m. Okay? Now, if we have a combination of waves, so if I have two waves, for example, the simplest wave that I could have, simplest wave packet that I could construct would be two waves with very similar, k and omega. So if I have one wave, for example, which goes like e to the I kx minus I omega t. And in addition to that, if I had a second wave, e to the I, okay, let me call this one k1 omega 1, k2 x minus omega 2 t, I omega 2 t, okay? So now this is sum of two waves, right? Okay, so I can now express this as the product of two waves, right? So I can write this as, let me see. Okay. It's usually better to use cosines and such things here, but let me just first look at something like this, e to the I k1 minus K2x, okay, minus I omega 1 minus omega 1 minus omega 2t. Okay, I'll multiply this with two terms so that I can get the proper term. Okay, so to convert this into that, this is just going to be a mathematical identity. We'll discuss what it means physically in a minute. So how do I get these things together? Let me also divide this by 2. Okay, so I'm going to get e to the I k1 plus k2 x over 2. Okay, and to get the omega 1, I need minus I omega 1 plus omega 2 t over 2. Okay, so now if you multiply these things together, if I did the algebra correctly, we are going to get the first term. Plus, yes?
Don't we need the t over 2 there in the first?
Yes, thank you. So it's going to be all parallel. And now over here, I'm going to try to get the K2. So it's going to be I K2 minus K1. Okay. So that if I multiply these things together, now I have, I'm going to get, okay, let's see. I told you I'm not good in algebra. Okay, so now minus. Okay, now we seem to be okay. Okay, so K1, K2. Now I want to get the K2 out. So this is going to be K2 minus K1 x over 2 minus I omega 2 minus omega 1 t over 2. Okay, you can just please check this out, multiply it out, should be okay. Okay, so if I multiply these things in the second term, the K2s add up, okay, but K1s cancel. Similarly, omega 2s will add up and omega 1s will cancel. It's going to be the other way around for that. Okay, so what this means is I'm going to get, really, this thing will look like, okay, two waves. And this thing, you see, everything comes with a plus sign and the minus sign. So this whole thing is just twice the cosine of K1 minus K2 over 2 x minus I omega 2 minus omega 1 over 2, right? Omega 1 minus omega 2 t. Okay, so what I have is a product of two waves. One wave is this one here. Okay, so if we try to find out the velocity of this wave, so if I want to analyze this wave, I can write this as I, okay, K1 plus K2, or, well, let me just keep the 1 over 2 over here. Okay, so K1 plus K2, and then I have, okay, over 2. Then I have x minus omega 1 plus omega 2 over k1 plus k2 t, right, for that wave. So if you just assume that k1 is close to k2, okay, so k1 and k2 together, so k1 plus k2 is approximately 1k, yes.
Also for the cosine there is no I.
Yeah, okay. Thank you. Okay, so this is going to be the form of the wave which was being multiplied by this wave. So I have some cosine function, okay, which does something like this. And you see that it's going to have a large wavelength because k1 is close to k2, right? So if k1 is close to k2, k1 minus k2, which is going to be the wavelength of this wave, which is equal to 2 pi over lambda, okay? So it's going to have a large lambda. Whereas this one will have, again, a wavelength which is approximately equal to the original wavelength. Well, it's going to have a wavelength. So here I have k1 plus k2 over 2. So these are two numbers which are close to one another. So their average is close to either one of them. So this is going to be, again, 2 pi over lambda. So this lambda is going to be small. So I'll have a complex wave with real and imaginary parts. Okay, so let me put them in different colors perhaps. Okay, so I have this wave, e to the I k1 plus k2 being multiplied by the cosine. So I get something like this. Okay, there's a real part and an imaginary part to it. Okay, so I'm just making this up, obviously, not drawing it very carefully. But this is the form of the wave. The envelope, okay, so is equal to this cosine function. Now, if you look at the velocity of the cosine function, so now I am going to write this as twice cosine k1 minus k2 over 2 x minus omega 1 minus omega 2 over k1 minus k2 t. All right. So you see the velocity of this wave, which we are going to call the group velocity, is equal to delta omega delta k. So in our case, remember that delta omega delta k, I have to find, so if I multiply by h bars, it's going to be delta energy over delta p. So I can write this as d dp of p squared over 2m, for which I end up with p over m. Okay, so I recover the classical velocity. So the envelope here, which really represents the motion of the particle, is moving with velocity, okay, p over m. So going back over here, we had this phase velocity, but as a whole, the object, the wave function, its envelope, moves with velocity v group. Now, this is a sort of approximate argument, because we know that, especially, for example, for the case of the Gaussian that we studied, the shape of the Gaussian was deforming, right? As a function of time, the shape of the Gaussian was deforming. Now, in the case of the Gaussian, things are even better than a general form. So if you take a general form of a wave function, as it moves in time, okay, so if this t equal to 0, at a later time, it's going to have a different shape. So it's a little difficult to define, associate a velocity with a shape that's changing all the time. Okay? But as a whole, these things tend to move in an approximate way with the group velocity, which goes like the derivative of, this is with respect to p, right? Derivative of the energy with respect to p. Okay, so derivative of p squared over 2m with respect to p gives you p over m. Okay, yes.
So Vg is the coefficient
Of t, yes.
V1 minus
Yes, so we get a form which looks like x minus v group t. Okay, so
By the way, why I couldn't understand well that why Vg is equal to P divided by M. I mean, V1 minus V2.
well, it's the derivative of p squared over 2m with respect to p. So you get p over m.
Ah, okay, I see.
Okay? Just derivative of energy with respect to p, yes.
I couldn't understand this. Why
Oh.
lambda over there is small and the other one is large?
Okay, so what we have done, remember how we construct these things. So let's just look at that. Okay, so we are constructing a psi of xt out of, there's 1 over square root of 2 pi, some g of k's and e to the I k x minus I, okay, omega sub k t type of forms, right? So this is the form of the general form of the psi. Now, what are we doing here? We are constructing a wave function out of waves with certain wavelengths. Now, if you, obviously g of k can be anything you like, but if g of k contains lots of wavelengths, then of course you don't have even a good shape to talk about. Okay, so what we are assuming here is that we have an object which has a specific shape which is moving with more or less without much deforming. Okay, so we have a psi of x0 which looks like this. At a later time it perhaps has spread out a little, so it's psi xt, but as a whole it seems to be moving along the x direction with some velocity which I can associate with a velocity. Okay, it's moving with some form so that I can associate a velocity with it. So that velocity I am going to call V group, so that this is V group times t. Okay, so now for that to happen, I must have a bunch of wavelengths here. Okay, and they are going to make up this waveform. Now, in this case, I'm looking at a special case, an extreme case, to understand what's going on, in which this g of k is really made up of two k's. So the analysis that I did there had these two wave functions. What does that mean? This g of k was really a delta function of k minus k1 plus delta k minus k2, right? So if I put that in here, I am going to get that, okay? So if I have only these two wavelengths, what does that correspond to as psi of x and t? According to that algebra I went through, it corresponds to, okay, an envelope which is limiting the oscillations of these waves with wavelength k. So if k1 and k2 are close to one another, this, what is making up this oscillation is approximately e to the I, one of the k's, x, okay? Doesn't matter whether it's k1 or k2 because I am assuming they are close to one another. Okay, but their envelope here is something which goes like cosine k1 minus k2 over 2 times x and the time dependence. So now if you look at this, k1 minus k2, if k1 is close to k2, k1 minus k2 is going to be quite small. And if that's, so this effective k, so k difference, whatever you want to call it, it corresponds to a wavelength, lambda, which is large. So that's the wavelength of this cosine wave. Okay, so that is going to be much larger compared to the wavelength of the k directly. Okay, so and now this thing moves. Okay, so this envelope itself moves with the group velocity. In this case, this doesn't. Okay, the envelope is not deformed. It goes without dispersion. Okay, other questions? All right, so next set of problems that we are going to discuss will be, okay, yes.
There are other waves other than the envelope, but we have only one wave in here.
Why? Why is there other, what other waves do we have?
Two different waves in the envelope, right?
Well, it's just e to the ikx, okay? It's just e to the ikx. So this is just e to the ikx, which has real and imaginary parts, okay? Okay. So next we are going to look at problems which involve 1D, okay? So this means one-dimensional scattering. Okay, so we are going to now start with simple problems in which we have free particle type of solutions to the Schrödinger equation at negative x and at positive x, but something in between, so that we are interested in how much of the particles are being reflected and how much is being transmitted. Okay, so the first example that we are going to discuss will be the scattering from a step potential like this. Okay, so suppose I have a step potential and someone is going to throw, okay, so here's our experimentalist, and she shoots particles into the barrier. Now, classically, what would happen if I have a barrier? So let's look at the classical experiment. So let's just smooth out this wall a little bit so that classically we avoid the finite size problems associated with the object. But suppose I have an object on this all frictionless surface, so that this is the potential energy, and I shoot it towards the right with some initial energy. Now, what happens? If this energy is sufficiently high to climb this barrier, it will pass towards the right, with 100% probability. There's no problem about it. But if it doesn't have sufficient energy, then it will be reflected back with 100% probability. Okay? So if I have a certain energy, okay, so if this is the, this is a plot of the potential energy as a function of x, and my energy is somewhere over here, okay, if that's my energy, the level of my energy, this point here, remember, is called the classical turning point. Why? Because at that point, the kinetic energy is equal to the potential energy, and the object comes to rest and then returns back. All this region here, okay, so this whole region over here is the classically forbidden region. Now we are going to see that if the particle that's shot into this barrier does not have enough energy, so if this is the level of the energy, and this is our v of x as a function of x, and v of x has value v0 for x greater than 0, so let me just write this. So v of x is equal to, okay, 0 for x less than 0, but v0 for x greater than 0. Okay, so this is the shape of my potential. Now we'll see that there will be a probability of finding the particle in this classically forbidden region. Okay, so it will sneak into the classically forbidden region, and we'll find out some probability of finding the particle there. So that will have consequences. For this problem, obviously the particle cannot go very far away, but we'll see that if this right-hand side is converted into something like a barrier, then the particle can actually go through that barrier, although it doesn't have sufficient energy. Okay, so that will be the next problem that we are going to solve. In any case, this is what we have. So the problem we have to solve in two versions. Let's first look at the case when E is less than V0. So these particles are being shot towards the right with an energy which is less than V0. Okay, so less than the height of the barrier. Okay, so what we'll do is, since this is a piecewise, okay, constant potential, we'll first solve the Schrödinger equation for this region. We'll solve the Schrödinger equation for that region, and then we'll match the solutions at the boundary so that we get a full solution. Okay? So over here, the Schrödinger equation is, the time-independent Schrödinger equation is minus h bar squared over 2m, right? d squared dx squared u is equal to EU. So I don't have any potential. Since I don't have any potential, that's all I have. Okay? So this we solved earlier. This is just a free particle solution. Minus 2me over h bar squared u. And the solutions were u is a linear combination of e to the I plus kx and e to the minus I kx, where k is equal to square root of 2me over h bar, right? Simple differential equation. Second derivative of this is going to bring down a minus k squared which is going to be equal to that. Okay? So that means I can write this expression. So for x less than 0, this is all that we are doing here is the case for x less than 0. This u of x is going to be a linear combination of e to the I kx and e to the minus I kx. Okay, so we discussed when we were deriving this equation for probability current what a wave function like that meant. Okay, so remember that this corresponds to a probability current, right? Remember that we had this prefactor in the front, h bar k, no, h bar, well, okay, in this case that's h bar k over m a squared coming from this term. But there was also a minus h bar k divided by m times b squared coming from the second term. So the a term, okay, e to the ikx term, a times e to the ikx term, corresponds to a probability flow from left to right. So that is what this experimenter is, okay, experimentalist is providing. Okay, so that is something that is being generated by the system, okay, whoever is sending these particles, that corresponds to that probability current towards the right. B is probability current towards the left. So that means if there is such a term here, that must mean particles are being reflected from this potential and are coming back. Okay? So the wave associated with A is called the incident wave. And B is the reflected wave. Okay, so that's what happens for x less than 0. What happens for x greater than 0? Well, we now have a different differential equation. We'll have minus h bar squared over 2m d squared dx squared u plus v0 u is equal to eu. Let me again move terms around. I'm going to get d squared u dx squared, okay, is equal to v0 minus e. Okay, if you keep track of the minus signs also, times 2m over h bar squared u. And remember that for x greater than 0, I have v0, and v0 is greater than e. So this is a positive quantity. Okay? So what are my solutions? Again, I'll have two solutions because the second order differential equation. What form of functions will I have on the right? Okay, exponential, but exponentials with real arguments, right? So it's going to be e to the plus k and e to the minus k, where k now is going to be equal to 2m v0 minus e square root divided by h bar. Okay? So if I evaluate the second derivative, it's going to bring down a k squared, which will be equal to this.
There is supposed to be an x there, right?
Where?
A,
Yes,
yeah.
of course. Thank you. Now, looking at the form of these functions, you see e to the plus kx. If I include that as a solution, that's going to go to infinity, right? So since that goes to infinity, I'm going to get a wave function which, well, it's not normalizable. I have lost all hope of normalizing this wave function since I am putting these e to the ikx type of functions on the left-hand side, but it will indicate a probability which is increasing the more you go to plus infinity, okay, which doesn't make sense. So this solution is not a valid solution. I throw that away, okay? All right, so on the right-hand side, I have a solution. My u is going to have a different constant, c e to the minus kx. Yes?
Can you again explain the why e to the kx is not a solution?
E to the kx is not a solution. Okay, so what type of wave function would I end up with if I allowed k? Okay, so if I now look at the magnitude of u, okay, as a magnitude squared is a function of x, this is where I have the barrier. So on the left-hand side, I am going to get some constant value. It's not going to be actually constant. It's going to be oscillating, but that's okay. So it's going to be this e to the ikx plus e to the minus ikx magnitude squared, which will give you an oscillatory function. And on the right-hand side, I want something. I'm looking for what the solution is. If I allow for e to the kx, it's going to give me a solution which goes like that. Okay? So it means probability of finding the particle is going to be larger and larger as I go into deeper and deeper into this classically forbidden region, which doesn't make sense. Okay? So that's why I'm throwing that away. So when I throw that away, I am left with e to the minus kx, which means that the probability will exponentially decay to 0, which makes a little bit more sense. Okay, so the particle is already someplace where it is forbidden to be according to classical mechanics, but just sneaks in as much as it could. Yes.
Shouldn't we have an I in the exponent of u e to the ikx?
Over here? No, because you see this is positive now. Okay, this v0 minus e is positive, so it's real. All right, how are we doing on time? Okay, let's then see what happens. All right, so I have two types of solutions, A e to the ikx plus b e to the minus ikx, and then there's this barrier, okay, at x equal to 0. And then to the right I have c e to the minus kx. Okay. Now, we'll have to match these solutions at the boundary. What do we mean by that? We have a wave function on the left-hand side which hits this barrier, okay? And I have a different wave function on the right okay, which extends to x positive. So at this point, okay, in order to have a consistent solution, I want whatever the probability current is going through into the barrier from the left to be equal to the probability current that's moving toward the right. Now, one way of doing that is to make sure that the u at 0 minus, which means at x a little less than 0, is equal to u at 0 plus, and the derivative okay, is also equal to, so we are making the function and its derivative continuous at that point. If you don't make the function continuous, then you are going to have a jump there with a gigantic derivative, which will mess things up. But if you have u and its derivative matched at the boundary, then remember what the current is. Current is h bar over m, imaginary part of u star du dx. Okay, so if you make u and its derivative continuous at the boundary, you are okay. We are also going to see, I put a vector, this is in one dimension. Okay, so we'll see when we get to the delta function potential that why this really has to be that way. Okay, so those are our matching conditions. So these are our matching conditions for the consistency of the wave function. Okay, so let's just apply them. When I set, okay, so u is continuous, means at x equal to 0, these things have the same value. So a plus b is equal to c. Okay, u prime is continuous, means derivative of this with respect to x, which brings down an ik. This will also bring down an ik, but with a minus sign. So let me factor that out. Ik plus a minus b is equal to, what do I have on the right-hand side?
Minus ck.
Okay, minus c times k, because differentiation with respect to x brings down a minus k, then x equal to 0. Okay, I have to put x equal to 0. That's what I have. All right, so I have two equations, but three variables, okay? But not really three unknowns. Why? Because A is a parameter, this experimentalist, wherever she is hiding right here, okay? A is a parameter where we are adjusting probability per unit time that's flowing towards the right. So everything, all the results will depend on A. So I treat A as a given, okay? So treat the incident probability current as given. Okay, so that means A is not an unknown, which means I have just two equations and two unknowns. So I'll have to solve everything in terms of A. Yes?
Also, what is the physical meaning of adjusting A? I mean, what the experimental does and change the A?
Okay, well, we are talking about a single particle system. So we, in essence, what we have here is the magnitude of the wave function that's coming in. Okay, so since this wave function cannot be normalized, it's not associated with a with a certain type of waveform. What we are doing here is to see if we wanted to solve a precise problem of a particle hitting this barrier, what should we do? We shouldn't really use a scattering wave function like this e to the ikx and e to the minus ikx. What we should do is we should put here a Gaussian, right? And okay, a Gaussian shaped wave packet and send that into the barrier. Then there will be no problem because this is well normalized and everything. And this would just, as a function of time, hit this barrier. Certain complicated things would happen. And then it would just bounce back and would be coming back. So we would need to solve that problem if you wanted to solve a particle hitting a barrier. But that's a difficult problem, okay? Even the Gaussian that we solved last time, which is moving in v equal to 0, did not give us very simple results. What we are doing here now is we are knowing that this wave packet is made up of lots of waves, okay? So this is g of k e to the I kx dk. We are really solving this problem for various values of e to the I kx separately, okay? Then, it's, as you'll see, it's going to be a much simpler problem. And that corresponds to a particle which is spread out from minus infinity to plus infinity, which you cannot experimentally generate, okay? But gives you nice, simple solutions. Then those solutions, if you like, you can put into this equation and obtain the time-dependent behavior of this wave packet. But since that's, okay, that's something if you want to do later on, you can do it. But at this stage, we are just going to be interested in a single wave like this, okay? So that single wave does not correspond to a single particle. But since the experiment involves shooting particles from the left, this parameter A, which is the incident wave, we assume is something that's, okay, under our control. So it's not an unknown. Okay? Okay? Okay, so okay, so maybe I shouldn't say this experimentalists can just turn a knob and adjust what A is, okay, but it's something still under our control, not an unknown. Okay, well, let me just finish this algebra and then we'll have the break. So this second equation I can write as A minus B is equal to, let's see, minus k over ik times c. So if I now add these two equations together, so that the b's cancel, I get 2a is equal to 1 minus k over ik times c, or c is equal to 2a over 1 minus k over ik. So that's one of our results. I have found what c is in terms of a. So if I want to find b, b is just equal to c minus a. So I just subtract 1 from this. So this is going to be 2 over 1 minus k over ik, and I subtract 1 from it, so it's 1 minus k over ik, and I end up with what? 1 plus k over ik, 1 minus ik over ik, okay, is equal to times a, which I forgot, times a is equal to b. Okay, so that's our b. Okay, so simple, just two equations, two unknowns. We solve them in terms of a, and that's what we get. Okay? Okay, let's have our break, and then we'll interpret these things.